Welcome to the next session of our discussion on the ultraviolet and visible spectrophotometry. In the last class, we have discussed about the molecular orbital theory, and we have shown that the bonds expected in organic compounds are of the type sigma to sigma star, that is a single bond, and pi to pi star, that is a double bond, and then there would be non bonding electrons which also can get excited to n2 sigma star and n2 pi star. So, these are the types of transitions expected in the organic compounds. And in general, I have already told you that n to pi star transitions are of least energy and pi to pi star transitions are of slightly higher energy, and n to sigma star are still higher, and sigma to sigma star would be occurring in the vacuum ultraviolet regions. Now, the question is it possible to correlate the structure of the organic compounds by relating to the peaks that are observed in ultraviolet and visible region? Mostly we will be discussing about the organic compounds in the ultraviolet region. So, this is what slide I had shown you in the last class, that is, if we have a CH3Cl, the lambda max expected is at 173 nanometers. For methanol, the lambda max is 183 nanometers. This would be because this is occurring in the ultraviolet range very near the end. This would be n2 sigma star transition. Similarly, in trimethylamine, there are only NH2 group, there is only one NH2 group, and then all other bonds are sigma bonds. That means there are no double bonds or triple bonds in this case. So, the only peak that is expected is n to sigma star, because sigma to sigma star transitions are not expected in UV region, and n to sigma star transition would be occurring at 227 nanometers, and epsilon would be 900, that is the molar extinction coefficient. Now, is it possible to correlate larger molecules if they could contribute to the lambda max? Now, I have given you in the last class this slide, that is known as WOODWARD-FIESER rules for dienes. So, dienes means alternate double bonds separated by a single bond. So, if we have a butadiene or parent butadiene or a cyclic conjugated diene, the peak expected is at 217. If both the double bonds are in the same ring, then we can expect the peak at 253, that is the basic this thing. Suppose there are substituents, these substituents will act to labelize the electrons, and then the lambda max is the energy of the system would be still lowered, and then they would be shifted to the longer wavelength. That means the lambda max would be shifted to longer wavelength. So, what would be the contribution? For each alkyl substituent or ring residue, we add 5 nanometers. That means, instead of 217, if there is an alkyl substituent, it will go up to 222 nanometers. Suppose there is an exocyclic double bond, then that also will contribute to the shifting of the lambda max by another 5 units. What is an exocyclic double bond? It is a double bond attached to a ring outside, and extended double bond is again the same diene system in which one more double bond is there separated by a single bond, that we call it as extended double bond. Now, there are some specific groups. For example, if it is O-alkyl group, that is for example OCH3, OC2H5, something like that, then that group will contribute to shift the lambda max by another 6 units. Then S-alkyl groups like SCH3 etc., they would contribute to shift it to the right side, that is wavelength side, by 30 nanometers. Chloride, bromide etc., they would shift it to by another 5 nanometers. N-alkyl groups would of course do it for up to 60 nanometers. Now, we will see another system. We have seen another system, that is alpha beta unsaturated ketones and aldehydes. They also show some sort of structural relationship to the ultraviolet lambda max position. Now, without any substituent, if we have an alpha beta unsaturated ketone, then the base value would be 215, and if it is located in a 5-membered ring, then it is 202 nanometers. Now, if it is an aldehyde, alpha beta unsaturated aldehyde, then you would expect the lambda max to be around 207 nanometers. Now, again substituents, if they are like this CH-COX, where X is an alkyl group, the base value itself would be 2 and 5, and if it is X is a hydroxyl group or an ester group, you would see that the base value would be somewhere around 193 nanometers. Now, if there is an exocyclic double bond, another 5 nanometers need to be added to locate the lambda max, and if there is an endocyclic double bond, another 5 nanometers to be added, and extended double bond as usual adds another 30 nanometers. Suppose there is an alkyl group or ring residue at the alpha position, then we have to add 10 nanometers. Suppose there is an alkyl group or ring residue at gamma or delta position, then it should be added another 18 nanometers here. Now, if it is a homodiene, you have to add a component of 39 nanometers. So, these are some of the systems. Now, I just would like to show you that pi to pi star transitions occurring in these situations, because this is butadiene, there is a double bond, single bond and double bond. So, for this lambda max would be 217 and epsilon would be 21,000, which means we will be having a very strong bind. Suppose it is hexatriene, that is 3 double bonds separated by this single bond and another single bond. There is an addition to the double lambda max by this third double bond, and it will be shifted to, it is shifted to 256 nanometers, and molar absorptivity is around 22,400. I have given you this table where the different lambda max have been recorded. More data can be had, some from the databases. If you look up any textbook for organic chemistry or spectrophotometry, you would see some more data which you can correlate to the transitions that are occurring in the ultraviolet region corresponding to sigma sigma star, n to sigma star, pi to pi star, etc. Now, you have to understand some of the important things. For example, the same compounds, suppose you take one compound in the vapor form, one compound as a liquid, that is neat form, or dissolve the compound in some other solvent, what type of lambda max you would be expecting, what type of ultraviolet spectrum. Now, in the you can easily expect that there would be molecular interactions, therefore, they show lambda max at slightly differing wavelengths. This is very important because one should not confuse that the peak corresponding to the lambda max could belong to some other compound. That is not correct. So, solvent effects are particularly severe for weak absorption bands. Sometimes weak bands disappear in more solar solvents, especially weak bands. If they are not easily visible, you change the solvent to more polar, they will completely disappear, and less polar, they could be still visible. Now, suppose you have similar compounds, same chromophoric group, then the lambda max need not show at the same wavelength. It could be shifted because the compound is similar, but not exactly same. Basically, what we expect is a chromophoric group like NH2 or OH group, etc. in C2 system, C3 system or C5 system. All of them need not show exactly the lambda max at the same wavelength. This point we will have to remember whenever we are doing some problems. And an isolate, what is a chromophore? I have already defined it earlier for you, and it means an isolated functional group not in conjugation with any other group is called a chromophore if it exhibits a characteristic absorption in UV visible region. Functional groups that do not show characteristic peak above 200 nanometer, but when attached to a chromophoric group in the compound, they do cause a shift in the absorption peak, that is lambda max, to longer wavelengths and increase its intensity. Such groups by themselves do not show a peak, but they will increase the lambda max. They are known as auxochromes, and examples are OH, NH2, SH, halogens, etc. So, this is what we have been discussing because of the presence of OH groups, NH2 groups, etc. That is, these auxochromes would rather tend to increase the lambda max to the longer wavelengths. Now, this is another system, alpha beta unsaturated acids and this thing. Here we have monosubstituted, disubstituted, and alpha beta and beta beta. That is, on the beta compound we have two substitutions, and then sometimes alpha beta and beta beta disubstituted. Extended double bond is 30, exocyclic double bond is 5, endocyclic is 5, gamma or delta substituted alkyl group is 18. Now, right now it may look slightly confusing to you, but when we solve some problems, we will be able to sort out very easily where the lambda max can occur. Now, you can see that here it is a system of double bonds, that is alpha beta unsaturated ketone we have already discussed, and aromatic systems we have benzene and several other systems. Aromatic systems, they show a strong absorption band at 184 nanometer with a molar absorptivity of 47,000 and 202 of 7,000 and a series of weak bands. These are associated with the vibrational effects on the pi to pi star transitions. Now, this is a figure which I wanted to show you. The top one is vapor form, the bottom one is in the liquid form of benzene aromatic system. So, you can see that peaks are sharper here, number of peaks are there 1, 2, here there is a 230, there is 1, 232, there is 1, 240, like that, about 7 to 8 peaks are there. But if you take a look at this spectrum in a solid as a liquid, you can see that all these fine structures are missing, and what you would be seeing is basically a simple broad peak that is there. So, substituted benzene rings also contribute to some extent the shift towards the longer wavelengths. For example, alkyl groups shift the lambda max to longer wavelengths known as bathochromic shift, and addition of second alkyl group at para position produces a bathochromic effect with increased epsilon. Orthoisomer shifts the lambda max to shorter wavelengths with reduced epsilon. Now, this is a benzene ring with COOH group. You can see that the lambda max is at 240 nanometers, and for the COOH group also there is lambda max at 240. Similarly, NH2 groups, OH groups, etc. shift the bands. These are different bands designated in the aromatic positions in the spectrum, bands to longer wavelengths, and kills the fine structure due to N to pi star transition. Now, this is organic effects of oxochromes I have listed here for you to appreciate the effect of the substituents and their change in the lambda max. Since we have already covered this, we will not go ahead discuss this further, and this also we have seen it. Now, let us try to solve some examples. Now, first example I have chosen is calculate the lambda max for 1,4-dihexacyclodiene. So, the structure is like this, and parent here you can see that diene system is like this, and here you can see the double bonds are separated here. There is 1, 2, 3 and 4. It is extended over 4 carbon atoms separated by a single bond between 2 and 3. So, the parent heterodiene lambda max would be is at 2 and 4, and then you can see that there are one substituent here, there is another substituent here, and then there is one more substituent here and there is one more substituent here. So, there are 4 substituents, and unlike if they are CH3 groups or C2H5 groups, etc., it is alkyl substituent. But even if it is not an alkyl substituent, just as shown here, we need to take this part of the ring as a substituent, and we have to calculate. So, that gives us alkyl substituents 4 are there, 1, 2, 3, 4 I have marked, and with the arrows, and that adds 20 nanometers, and there is one exocyclic double bond, that is this double bond. To the right side ring, that is a double bond attached outside the ring to the outside the ring, but still into the diene system. So, that is known as exocyclic double bond. So, this double bond adds another 5. So, there are 2 exocyclic double bonds, that makes it. So, that makes it 244 nanometers. So, let us take another compound like this. There are 3 cyclohexane rings, and there is a double bond system here, here and here, and now if the basic base value is 253 nanometers, because there is a double bond in the same ring, and this is known as homoannular diene. And so now you may say that there is a double bond system that is not in the ring. Suppose we take this range, then we have it is a heteroannular diene. This could be a confusion for you, because whether to whether to choose that color, that heteroannular dyne or this dyne. This part or this part. This is a heteroannular, this is homoannular dyne, and this is the heteroannular dyne. Now, which one to take is the question. The question is whichever is higher value, you take that. So, the basically what we choose is a heteroannular dyne, and its base value is 253 nanometers. Now, there are ring residues. For example, here how many substituents are there? This is 1, this is 2, this is 3, this is 4. That is we have a figure like this. And one more is here, double bond. So, this is the homoannular dyne, this is carbon number 1, 2, 3, 4, 5, 6, like that. There is 2 substituents here on carbon number 1, and then there is 1 substituent on carbon number 4, and 1 substituent on carbon number here, and another substituent here. So, how many substituents are there? 5 substituents. Five substituents are there. 1 is here, 2, then 3, and then 4. This is 5th one. So, if you take 5 into 5, that would be 20, that will add to the lambda max of 25 nanometers, and there is one exocyclic double bond, because this double bond is outside the ring but attached directly to the double bond. So, this one. So, that will add up to 5, and then you can see that this double bond is exocyclic to this ring. So, one more, and this double bond is exocyclic to the middle ring. So, there are 3 exocyclic double bonds, that is, it will add 15 nanometers. Now, there is one extended double bond. If you take this homoannular dyne, it is separated by one single bond and again another double bond, that is, the lability is increased. So, this will add to the shifting of the lambda max by adding another 30 nanometers. So, if you add up all this, it is lambda max works out to 323 nanometers. Now, what is the observed value? You can see here it is 320. So, you can see how closely there is a match between the calculated and observed values. Now, let us take another example. that is calculate the absorption now maximum for 4-cyclohexenyl 2-pentene. This is cyclohexenyl group, and then there is a double bond, and this is one substituent, and then a double bond between carbon number 3 and 2, and there is one CH3 group at the end, and this double bond is separated by this double bond by a single bond. That means it is a diene system, because they are basically no other functional groups. So, we call it a diene system, and it is a 2,4 diene system, because I have put numbers here 1, 2, 3, 4. So, 2 it starts, double bond starts from here, 4 double bond starts from here. So, it is a 2,4 diene system. So, the base value for a diene system is 217 nanometers. Now, how many substituents are there? Alkyl substituents. There is one here, alkyl, so that is methyl group. On carbon atom number 4, there is another substituent. So, 2 alkyl substituents are there, that adds 20, and then on this carbon atom there are 2 bonds, one here and one here. So, these 2 will add another 5 nanometers. So, that will that we call it as ring residue, and that will add another 10 nanometers, and then this double bond is attached to this ring outside, from outside. So, it is an exocyclic double bond. So, if you add up all these things, there are no other contributions. So, if you add up all these things, it works out to 242 nanometers. If you take the spectrum once again in solution, what you observed value is 242 nanometers. See how closely these things show the lability which can be attributed directly to the observed and calculated values. It is a beautiful system basically. You would really enjoy working with some more examples and see the correlation between the structure and the lambda max. Now, take this example, lambda max for the for this compound. Now, you can see that there are 4 compounds, 4 rings, 1, 2, 3, 4 and there are 4 double bonds in this compound, and 2 of them are in the same ring, this one and this one. So, it is a homoannular diene, and this ring is a extended double bond, and then there is another extended double bond here. So, let us calculate. Base value is 253, 2 extended double bonds 60 nanometers, 3 ring residues, 5 ring residues 25 nanometers, 1 exocyclic double bond is 5 nanometers, and calculated value is 343 and observed value is 345. Again, a very close matching has been observed in this system. So, let us take one more example. This is a ketonic system, and there is one double bond. It is an alpha beta saturated ketone, base value is 2 and 5, beta substituent is 12. There is one delta substituent, that is 18, conjugated double bonds there are 2. So, it is 60 nanometers, contribution from the homoannular diene is 39, exocyclic double bond is 1:5, 1:5, so to 349, and the observed value is 348 nanometers. Now, you calculate the lambda max for this compound. It is a cyclopentenone system, alpha beta unsaturated cyclopentenone, and here is the parent value is 202 and beta substituent. These things you can work out yourselves. Ring residue at gamma and delta, there are 36, extended double bond is 30, one exocyclic double bond is 5, so 285 is total value, whereas observed value is 287. So this paracyclochloroacetophenone is my next example which I have chosen for you, and here you can see this is an aromatic ring now. It is not a diene system or triene system, because it is an aromatic ring. There is acetophenone group here and there is one chloro group here. Now the parent value for an aromatic system is 246. There is one chlorine atom at the para position, that is 1, 2, 3. It is a 6-membered ring. Opposite side is para and next to adjacent sides are ortho, and these two sides, other two are meta, ortho, meta, para. Again meta, ortho and para, like this. So the expected value is 256 and observed value is 254 nanometers. Very good correlation. Now we will take another example, that is 3,4-dihydroxy acetophenone benzene ring. This is acetophenone group. 3,4-dihydroxy, there are 2 hydroxyl groups, 1, 2, 3 and 4. So it is a 3,4-dihydroxy, 2 hydroxyl groups attached to that. The base value is 246. There is 2, 4 means 1, 2, the meta value, a hydroxy group at the meta position. This adds only 7 nanometers because it does not actually get involved into the labilization of the electrons, non-bonding electrons present on oxygen, to shift it to longer wavelengths because of the steric hindrance. But para-hydroxy adds quite a lot, that is 1 into 25 nanometers. So that is 25. So total calculated value is 278 and observed value is 281. Again there is a very close matching between these things. So like this, a great number of information, a great deal of information about an unknown compound can be deduced from UV visible spectrum. For example, you can see that if you do not get any spectrum, any peaks in the ultraviolet region, then you can safely conclude that it could be a hydrocarbon and then it does not have any functional groups such as methyl groups, alcoholic groups, hydroxy groups, NH2 groups and several other functional groups you can straight away eliminate. And if the spectrum actually indicates the absence of peaks, elimination of a large number of functional groups is possible. This is very simple to understand. If there is a peak, there is a chromophore, and then if there is a chromophore, there has to be a peak. If the compound is saturated, the compound without any substituent, basically it means that there are no substituents, and no substituent means no peak. If there is a substituent, you will get a peak, and if the substituent, to get a peak, the substituent should be a chromophore, and suppose the chromophore alone is not there. For example, no chromophore, that means no UV spectrum. It could be a transparent solution or substance which can be used as a solvent for other substances, because this does not show any peak. So the whatever peaks you can determine for an unknown compound would correspond only to that. So a substance which does not show any peak in UV region or visible region, again it means that they can be used as solvents. Now if the substance is indicates the presence of chromophore, then we can match the lambda max with the standard compilations, and additional information can be ascertained from the shape of the peaks, intensity and locations. For example, I have showed you the peak of benzene. If it is in vapor form, you would see you remember that you have seen it as sharp peaks. So, any substance which shows very sharp peak could be in the form of a vapor. Suppose it shows very broad peaks, then it is a solvent. The spectrum has been taken from the solvent. So, the intensity, suppose the substance it gives a molar absorptivity is very high, you will get a very sharp peak and very tall peak with large surface, with large peak area. That means there is a good chromophore which can be a characteristic of the substance, and then location of the peaks, that is also very important. Suppose you have a cis and trans isomer, then it is possible to determine which is cis and which is trans only by the use of ultraviolet and visible spectrophotometry. Now, the hindered rotations in biphenyl group. Now, this figure, suppose there is a group here and another group here, it is known as trans, and a group on the same side, these two are cis. So, the substituents we can always check whether it is cis or trans by the positions of the peaks, hindered rotation, coplanarity in molecules, etc. All these things information about such things can be obtained by some of the techniques using UV visible spectrum. Now, it is time for us to look at inorganic compounds. Now, we know that all organic compounds show some absorbance or the other in the UV region. It may be near the end point or it may not be near the end point, near the end absorption. Now, what about inorganic compounds? The inorganic compounds by themselves are not really colored. So, of course, you would know several inorganic compounds which are colored. For example, potassium permanganate, it is violet in color. If you take a small quantity of potassium permanganate, when you buy from a shop and just put it in water, it will show violet colored solution, and it is a permanganate ion that is responsible for the color. Similarly, you have dichromate, potassium dichromate, that is a yellow colored solution. Copper salts, in general they are all blue colored, and if you dissolve it in water, it will give you a blue colored solution. Cobalt, nickel, some of these things are colored solutions, but several elements and metal salts are colorless. Now, what happens to the determination of such compound? Do they show an ultraviolet and visible spectrum or not is the question. The answer is they do show, provided you convert them into a colored substance by a chemical reaction. So, the colored compounds in general of the inorganic substances consist of a charge transfer complex of an electronic donor group bonded to an electron acceptor, that is, one has to be a donor, one has to be an acceptor. Now, when the product absorbs radiation, an electron from the donor is transferred to the orbital of the acceptor. Now, this is somewhat akin to charge transfer. So, this situation is somewhat akin to an internal redox process. So, charge transfer bands have high molar absorptivities of the order of 10 raised to 4 to 10 raised to 5. Now, you would remember that molar absorptivities of 10 raised to 4 and 10 raised to 5 range are basically very strong absorption bands. So, it is possible to determine the substances in very low and small quantities. The complexes generally absorb at longer wavelengths, that means they are all in the visible range. Now, some of the well known charge transfer complexes are like this: benzene and iodine. You just take a little quantity of iodine into put it in benzene, it will be brown colored. So, this brown colored solution is basically a charge transfer complex, and it shows a lambda max of about 300 nanometers. And aniline tetracyanoethylene is another charge transfer complex which shows lambda max at 280, 300, 610 nanometers. Naphthalene picric acid is another one, ferric thiocyanate and ferric orthophenone, the ferrous orthophenanthroline system, and iodine to iodide, iodine iodide system, quinhydrone hydroquinone systems. These are all basically charge transfer complexes. The first three examples are organic charge transfer complexes. That means there is no reaction as such in between between these two substances, that is benzene iodine. There is no reaction, but it does show a colored compound because of the charge transfer effects. And whenever charge transfer effects involve metal ions like this, iron and then dichromate, permanganate, etc., with ligands containing thiocyanate, orthophenanthroline, iodine, etc., iodide, these things will show in general lambda max in the visible region, and some of them do serve as an electron acceptor. That means it is a Lewis acid. That Lewis acid is one which accepts electron. Perhaps the greatest applications of ultraviolet and visible spectrophotometry are in the qualitative and quantitative analysis of organic, inorganic and biochemical compounds. You would appreciate that actually there are more than 30 million spectrophotometric analysis are being performed every day all over the world for the determination of organic compounds, inorganic compounds, biochemical compounds. Organic compounds, you can understand that most of them are in the containing only carbon, hydrogen and some functional groups. Inorganic compounds, they represent almost all the elements of the periodic table what we come across in our day to day applications, except radioactive elements. And biochemical, blood, urine, plasma and semen, hair and body parts, and such the biochemical compounds are also amenable to spectrophotometry by ultraviolet and visible spectrophotometry. But as I told you, inorganic compounds by themselves may not have chromophore, but they can undergo a whole gamut of chemical reactions, hundreds and thousands of chemical reactions, which by which they end up giving colored complexes. And once you get a colored complex, you can be sure that an ultraviolet and visible spectrophotometric procedure is possible for the determination of the colored compound. Whether it is whether you relate it to the colored compound as such or species, original species, it is up to you. And in general, the determinations do not specify which one is which, but you can always correlate it to the original parent compound in which you are compound or an element in which you are interested. So, almost all elements, what is our conclusion? Almost all elements of the periodic table except radioactive elements in the periodic table can be estimated in this way. Permanganate and dichromate are the examples of charge transfer complexes with incomplete d and f orbitals. So, in the charge transfer can take place between the incomplete D and F orbitals and the ligand. Apart from such cases, redox reactions in which either of the products, redox reaction means one is oxidation, another is reduction. So if the compound could be, if a compound is oxidizing, it may be colored, and an oxidizing compound reduces the color in another substance, because these are redox reactions do not occur singly. If one compound has to be oxidized, a reducing compound has to be there. So they are always in pairs. That is why we call them redox reactions. So in redox reactions in which the product could be colored or the reactants are colored. Suppose the products are colored and reactants are not colored, then products can be estimated and reactants can be estimated, or reactants are colored and products are not colored. That is also another possibility. So such reactions can also be used for spectrophotometric analysis. Now, what are the types of reactions that things we can do? Reactions. One is catalytic reactions. You need a very small quantity of the catalyst to continue the reaction. So what happens? Catalytic reactions can be monitored by ultraviolet and visible spectrophotometry, and then you can do the determination of the stoichiometry. Suppose you want to know what is the ratio of the metal to the ligand in a given compound. So that you can do determine by spectrophotometry, or you can do the kinetic reaction rate monitoring. This is also very nice, easy to determine, because as if the products are colored, as the reaction rate increases, the product color will increase and you can monitor the color of the substance. Similarly, biochemical and enzymatic reactions, these can be monitored, provided one of the reactants or products has to be colored. That we should not forget. That is basically a fundamental requirement, that especially in visible region, it has to be colored. One of the 7 colors of the rainbow: yellow, red, or green, blue, and orange, purple, and all those things. Then you can do the diagnostic analysis, such as blood analysis, urine analysis, etc. That is also all in all, we can determine the compounds, inorganic and organic compounds, in several systems, and the chemical reactions play a very important role in the analysis of inorganic compounds. What you should be doing basically is, you have to have a proper choice of the chemical reaction and optimization of the important parameters to carry out a chemical reaction. What are the parameters? One is pH, another is reagent concentration, reaction time, temperature, order of mixing, stability of the complex, effect of other matrix components, ionic strength, statistical evaluation of the data, etc. You have to look at all these things if you want to standardize a spectrophotometric method, that is UV visible spectrophotometric method. So once a method is standardized, spectrophotometry provides an easy, sensitive, rapid and cost effective method to determine minute quantities of substances in either in microgram level or in submicrogram level, and sometimes nanogram levels also. It is very important. And then you can, some of the compounds which are not so colored, in for example copper salts, naturally colored, but their concentrations you can determine even in milligram quantities. They are also important in day to day chemical analysis, but they provide a very easy method. So the further improvements in sensitivity also can be brought about, that is molar extinction coefficient can be further improved by pre-concentration techniques, solvent extraction, chromatographic separations, and a host of other related techniques. Why do you need to do pre-concentration? Very important, but the requirement would be there if you want to determine gold in a in an ore, for example. The presence of gold would be of the order of about 1 or 2 micrograms per gram. So, if you want to determine gold, it is essential to separate all other compounds except gold and try to concentrate gold in a small solution or in a button, lead button, and that is where the pre-concentration techniques comes. Sometimes you may not, there may be too many other things in a given system. So, for example, if you want to determine gold again in seawater. So, you would appreciate that the seawater composition is a very complex one, and it contains 3.5% of sodium chloride. Now, gold would be in nanograms or picogram level, and if you want to determine picogram level in presence of percentage levels, you can imagine how much the effect they could have, and a solvent extraction of gold would help in separating it from all other substances. Similarly, separations can be achieved from chromatographic separations, and a host of other related techniques would help in sorting out the chemical analysis. Now, this brings us to the end of the discussion, that is at least the theoretical discussions about the spectrophotometry. But now let us look at the practice of spectrophotometry and the theory of spectrophotometry. What we are trying to do is to arrive at a relationship between the absorbance, that is, or transmittance of a given sample, and how it is related to the radiation. Now, that is what we are essentially discussing now. For example, spectrophotometry is based on the measurement of the fraction of light of a given wavelength transmitted or absorbed as it passes through solutions contained in a transparent cell. Imagine this is a transparent cell, radiation is coming through this, and then this cell contains your solution, and then it passes out. So, in the process, this solution would absorb part of the radiation, and then it will what is not absorbed is sent out. So, your initial radiation, that is P0, and transmitted radiation P can be correlated by the quantity of the substance that is present in this box, and since the box is having exact dimensions, the path length can be very accurately measured, and the concentration can be determined, and the determination can be quantified using all these techniques, and there could be they can be correlated using the using simple mathematical operations, which is known as Beer-Lambert's law, and that derivation and other related aspects we will see in the next class.